practical we're going to do today is to determine which type of crisps are a better fuel. So we're going to look at food as a source of fuel. Now this is quite a simple practical. I've got all the equipment that we're going to need set up ready. So I've just got tap water in a beaker and I've added this to a measuring cylinder to measure out 10 mils or 10 centimeters cubed, same thing, exactly, and then I poured this into a test tube. Notice how I've clamped it. The test tube is pointing away from me. So if you're doing this practically in a lab, you do not point the test tube towards your face or towards anyone else's. Next I'm going to select a piece of food and record the mass. So I'll start with this one. So we light the food. Once it's on fire, we place it directly under the test tube and we heat the water with the flame. So I'm going to wait until it's completely burned and then record the final temperature of the water. And notice I'm holding it over the heat-proof mat, not the clamp stand, so that if it does fall off this needle, then it lands on the heat-proof mat, which is safer. And if the flame goes out, we just relight it. Whoops. Okay, so that's just the oil. Oh dear. So risk here is melting the plastic of the needle, but we're alright. Oh dear, it's caught fire. Okay, so what I've done is I realised that I needed the mass of the crisp after burning because it didn't all entirely burn. Plus I had that scenario, that kerfuffle with the needle, which I won't be using. I'm going to use a different one for the next one. So I've amended my results table to make it better and transferred my results across. So I've added 2 new rows, final mass of crisp and mass of crisp burnt. And what I'd like you to do is subtract initial mass, take away final mass of the crisp to get the mass of the crisp burnt, and subtract final temperature, take away initial temperature to get the change in temperature delta T. And then you can work out heat absorbed by the water, just like we did with the alcohols experiment. It's the same equation, Q equals mc delta T. 10 because 10 centimeters cubed of water is equal to 10 grams. 4.18, that's the specific heat capacity of water, times by the delta T that we get here. And then lastly, we're going to work out the heat absorbed by water per gram of food by doing Q that we get here divided by the mass of crisp burnt, which is this row. So we're going to use this answer here. As you can see, this practical gets quite messy, especially if you're using oily, fatty foods. So I'm going to weigh the next crisp, pop it on the mass balance, and record the mass once it stabilises. 1.650 grams. I've got a fresh test tube with fresh water, new needle. Hopefully this one will be much better. And my food is mounted on the needle ready. Now I'm just going to light it. So we pop the weighing boat on the mass balance, press T for tare, which zeroes the mass, We wait for our crisp to cool down a little bit just so it won't melt this plastic, and when it's cool enough we pop it on there and record the mass of the burnt crisp. 0.756 grams. We get another fresh test tube, pop the thermometer inside, leave that there for a couple of minutes to stabilise, then we record the initial temperature. And now I'm going to record the mass of the last of this type of crisp. .606 grams. Okay, so I'll pop that down on the heat-proof mat, leave it to cool a little bit, then I'll record its final mass. We also need the final temperature, which is 40.2 degrees. So check your results with these. You should have got these results. As you can see, crisp 2 and 3, so this repeat and this repeat, the second and third runs if you like, released a lot more energy than the first crisp. And if we look at the test tubes that we used, we can see that a lot more soot was produced for crisp 2 and crisp 3 compared to the first one. Why do you think this might be? Now we're ready to start with our second type of crisp, the popcorn. I've got a fresh test tube, fresh water. I'm just taking the initial temperature, it's been there a couple of minutes, and I'm about to record the initial mass of this crisp. So our initial temperature has dropped slightly. It's now 14.2 degrees and it has been stable like that for a minute or so. So this one burns so quickly I barely had time to pick my camera up in time to record it before it was gone. So our final temperature is 22.1 and our final mass is 0.021. So for the last one, we've done 3 of each type of crisp now, and the initial temperature for crisp number 2 experiment 3 was 15.9. I did change the water, but the room temperature had just gone up slightly. So we put the weighing boat back on the mass balance. We press tare to zero it. And then we pop our burnt crisp into that weighing boat to record the mass. 0.013. Oh, wait till it stabilizes. 0.015. Okay. 0.017 grams. And just like we did before, I'd like you to work out the mass of crisp burnt, the temperature change for each of these 3 runs, heat absorbed by the water using your delta T values, and heat absorbed per gram of food using this mass of burnt crisp here. So now we have our completed results. Check your answers with the answers on here, and you'll notice that popcorn generally released more energy and is a better fuel for hikers compared to mini cheddars. Is that what you expected? is that what you predicted in your hypothesis? And we can also see that we've got one anomaly for each kind of crisp. So this one here is the anomaly, the first experiment for the mini cheddars. And this second one here is definitely the anomaly for the popcorn. So we can highlight those. The next thing I'd like you to do is write the discussion and conclusion for this experiment using the framework here.